So we sort of had people walking in for the birthday problem. Remember, the birthday problem is like, how many people until a repeat birthday? How many people until a repeat birthday? And this is a little bit like saying how many cards you need to be dealt until you have 2 of one suit. And last time I drew this tree like this. Let's draw it a little bit better. So the people sort of walk in. There's person number 1, person number 2, and person number 3, person number 4, and so on. And the way we set this up is we think of them as walking in one by one, and they each kind of look backwards at all of the people before them. So person 1 looks backwards at nothing, person 2 looks backwards at person 1, person 3 looks backwards at persons 1 and 2, and we ask, does that person have the same birthday as someone that came before them? Okay. And this gives you a probability tree. So you start with nothing. The first person, they, with a 100% chance, they have a unique birthday. So the probability the first person has a unique birthday is 100%. So UI is, or UN is the probability the nth person has a unique birthday. So U1 equals person 1 is unique. I shouldn't say they're unique. Everybody is unique, of course. I mean their birthdays. All right. Has unique birthday. I'll say has unique, and you need to know what I'm talking about. Okay. Has unique. It's like all your base are belong to us. All your birthday is unique. Person 2 has unique, etc. And yeah, the precise thing is in the mathematize. So person 1 definitely has a unique birthday. So the chance they don't have a unique birthday is 0%. Person 2, conditionally on the event that person 1's birthday was unique, of course that always happens, but given that person 1 had a unique birthday, the chance that person 2 has a unique birthday is not quite 100%, because there is a small chance that these first 2 people walk in the room and they both have the same birthday. And in fact, the chance is 364 out of 365. And that's because there are 365 days in a year. The chance that they have the same birthday is 1 out of 364. 1 out of 365, rather. And that's because whatever person 1's birthday is, there's a 1 in 365 chance that person 2 has the same birthday as person 1. So the way this tree works is the main branch, the going straight branch, is all the uniques, and then you have these like side branches coming off that are like, oh, we had a repeat. And really the question of the birthday problem is like, how far into the probability tree do you need to go before you take the off branch and somebody has a repeat birthday? So this was the setup from last time. Last time we said it's being done without replacement, right? So that's why we have dividing by 365. Every single person has 365 possibilities for their birthday, and it's not like the number of cards in the deck is going down. Every time you get a new person, you get a whole new birthday. This was all the setup, I think, from last time. Any questions or comments about this from last time? I think one of the new things is the notation. I don't know if I called them U1, U2 last time. So let's go. The mathematized question has the more precise version of these birthdays. So yeah, let's read these. So U1 is the event. The first person doesn't share a birthday with the previous people in the room. In other words, the first person has a unique birthday, so to speak. U2 is the second person, doesn't share a birthday with the previous people in the room. U2 has a unique birthday, and so on. And unique means with the people behind them, right? What we would like to find is the probability that U1 intersect U2 intersect U3, they all have unique birthdays. That's what we're looking for when we're trying to figure out the probability that 2 of them share a birthday. So that's the setup. Last chance for questions about the setup. I'm gonna ask you a question to fill in the thing in a second. So this is your chance to clarify if it's not making sense. All right, so if it is making sense, you should be able to fill out the next branch of the tree. So for the third person, right? For the third person, what is their probability of going in? I guess I only have 3 people here. Let's move the third person over a little bit. So the third person looks at the first 2 people, and the third person is thinking, is my birthday unique, or do I share a birthday with one of these 2 people? And if you're on this branch of the tree, you know already that these two people have unique birthdays, and now you're in the third branch of the tree. And so, like we always do in these things, we're finding the probability the third person has a unique birthday, condition that we made it this far into the tree. So the first person had to have one, the second person also had to have one, so we're doing U3 given U1 and U2. So that's the notation. And there's 365 days in a year, so it's something divided by 365. And the opposite is R3. R stands for repeat, so does the third person have a repeat birthday? That's also something out of 365. And your job is to fill in what these are. So fill these in on Math and Facts. Is the question clear? All right, I'm going to set you free on the question. Take a few minutes. Feel free to discuss. If you're totally lost, maybe the person next to you can help. Okay, there's like 30 seconds left. Who needs more time? More time, anybody? Okay, let's take a 30 seconds, put in your guess. If you don't know, it's okay. I want to see how many people know. Because if you kind of know, it's quick. It shouldn't take you a long time. If you're totally stumped, that's okay. Put in 111 if you're totally stumped. And that will help me understand how people are doing. Okay, so time's up. Let's see what people entered. All right, so what's the probability they have a unique birthday? Almost 70 people out of 80 said 363. That's most people, 70 people. Okay, wonderful. I guess if you said 363 ways for it to come out one way, then the opposite of 363 should be the number 2. 2 was the most common. And both of those are correct. So I think lots of people got that right. 363 one way, 2 the other way. That is the right answer. So 363 and 2. Okay. And hopefully you thought about it and figured out why. Basically, the first two people, they have 2 different birthdays. We know that they have 2 unique birthdays because we're conditioning on the event U1 intersect U2. So we know for sure that person 1 and person 2 both have their unique birthdays. Out of the whole calendar year, person 1 and person 2 are taking up 2 days. Whatever 2 days they're taking up, if we get one of those, we're out. We have a repeat birthday. If we don't get one of those, then there's 363 other days in the calendar that we could be in, and it all makes sense. You might think, okay, this is all so boring, and like, of course it's 363. But the thing I want to point out to you is that actually the genius of our solution is setting up the probability tree this way, right? Because if I just ask you, what is the probability of U3 on its own? This is a really hard problem. If you try to directly calculate the probability of U3, there's all sorts of weird cases. Because maybe U1 and U2 have the same birthday. And then it's like 364 out of 365. So like this on its own is difficult to calculate. But we've arranged everything in the probability tree so that when we get to here in the probability tree, we definitely know it's 363. So that was the smart thing. It's the way the tree is created is to set up this conditioning, and we're conditioning exactly on the kind of nice event we need of U1 intersect U2, that the first two people have taken up exactly 2 days out of the calendar, and that's what lets us calculate this. All right, this is like the genius, the unspoken genius of probability trees, is letting you do this kind of thing. But now that you have this, you can calculate the intersection that we're looking for. So this is too hard to do on its own, too hard. But what we actually want, we have everything we need to get what we want. So we want the probability of U1 intersect U2 intersect U3. This is the probability that all 3 people have different birthdays. Different birthdays. Okay, and that's because U1 has a different birthday than the people before them, U2 is different than the people before them, U3 is different than the people before them. Everybody has a different birthday. Okay, and by our probability tree, that is exactly this nice path over here. U1, U2, U3, they're exactly in order. We're going to multiply them all. That's the rule that we developed. So this is the probability of U1 times the probability of U2 given U1 times the probability of U3 given U1 and U2. It's exactly going along the top of the path. Okay, and this is nice. We can do 1 times 364 out of 365 times 363 out of 365. And that's the answer. The probability, if you have 3 people and the probability they all have different birthdays, is this product. It's very close to 1. This number is like 99%. This number is like 99%. You multiply them together, it's like 98%. But still very likely that 3 people in a room all have different birthdays. That's what we figured out. Questions or comments about any of the setup, about the probability tree or the calculation? All right, the next thing we're going to do is we're going to do it for more people. So how about 10 people? What's the probability? What's the probability of 10 people? So we'll have a U1 intersect U2 intersect. This is something mathematicians like to do. Dot, 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 intersect U10. This is if 10 people walked into the room, what is the probability that all 10 people have different birthdays? Okay, it's going to be something. I'll let you guys have a minute to think about it. You can probably look, if you're clever and like good at tests, you'll like look at this and you'll see the pattern, and you can probably fill in the pattern and get the right answer. Try to also understand what is going on. Like why is the pattern happening the way it is? That's the thing we want you to see. Okay, but take a minute, take a guess as what this will be, and then we'll take it up. I'll tell you the answer in a minute. Okay, let's take a look at this. So with 3 people, it was the product of 3 things, because you have 3 layers of branches on your probability tree. I did set it up so the first layer is kind of a silly layer, but that kind of keeps my head on straight. This one is going to have 10 layers. So you can imagine the probability tree is 10 layers deep, right? So there's the first person, There's the second person, the third person. This is like U1, U2, U3, and then there's dot, 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 all the way up to U10. 10 layers of my tree. And when I go to calculate this thing, it's going to be the product of these 10 numbers, these 10 conditional probabilities. So it's going to be probability of U1, probability of U2 given U1, probability of U3 given U1 and U2, dot, 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 all the way up to the probability of U10 given U1 and U2, and dot, 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 all the way up to U9. Okay? So it's a big product of 10 things. Mathematicians have like scary notation they use for this stuff. Oh, I said scary notation, I got beeped out. Okay, maybe I won't show you the scary notation. Okay, so this is totally optional. We won't make you use this, but if you like scary notation, you might have seen a big Greek S like this. This stands for sum. This is S for sum. Are we summing something here? No, we're not. We're multiplying stuff. So what do mathematicians do? They do a big Greek letter for P. What is the Greek letter for P? It's pi. So you do like the world's biggest pi. All right? And you put pi from I equals 1 to 10. You do the probability of UI given U1 intersect U2 intersect UI minus 1. So if you want, you can do this. This is like a little counter. It's like a little for loop that is counting up what we're doing. If you don't like this big scary notation, just write it out this way. It's totally legit. Okay, but that might be fun for some of you. Big capital pi. Okay, what is the answer? You can fill in these numbers. It's 1 times 364 over 365 times 363 over 365 times dot, 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 dot. And then the last number, every time the top of the branch always goes down by 1. And that's because the probability that the some guy, let's say U8, given all the guys before them, all the people before them have unique birthdays, the probability that the next person has a unique birthday is 365 minus the number of people in line. So it's always going down by 1 because the 7 people before the 8th person take up 7 days on the calendar, so there's 365 minus 7 days left that are all legit. Okay, so the final number here should be 365 minus 9 divided by 365 because there's nine people that were in the room before, and they take up 9 days on the calendar. You have to multiply all these numbers together following the pattern, and that is the answer. Okay, so that's like how you would do it. If you're going to type it on your calculator, you're going to be there for a while typing in 9 numbers and multiplying them all together, but we have the answer in principle. Any questions or comments so far? All right, so we kind of have the theoretical answer. It's still a little bit cryptic because it's like we haven't answered the original question, which is how many people will it take, right? So for any fixed number of people, we can say what's the probability it takes 10 people or less than 10 people. But like, how do we answer this kind of question? And what I'm going to do is I'm going to get the computer to calculate these numbers. And then we'll look at the computer answers and sort of get an idea of where do these numbers, how big are they for what values of number of people, and that will sort of answer the question. So that's what I'm going to do next. I'm going to put this in my calculator, but in a smart way on a computer. Questions or comments so far? All right. The easiest way to do math on your computer is a calculator. The second easiest way is spreadsheet. So that's what I'm going to do. Spreadsheet. This is like the computing tool of champions is a spreadsheet. Hopefully everybody's used a spreadsheet. Put your hand up if you've used a spreadsheet before. Okay, fantastic. I feel like sometimes I make a joke about like you know the movie Mean Girls and nobody's seen it, and I'm like, what universe am I living in? But okay, you guys have all used spreadsheets. Okay, so what's going to go in my spreadsheet? The person number, and the person number starts at 1. This is some kind of like heading, and it goes 1, 2, 3, 4. How do you make the spreadsheet enter in numbers? You put an equals the number above it plus 1, and then you go down. Okay, we have the first few people. Let's go down to like how big do I want to go here? Let's go to like 30 people. on my tiny little screen. Maybe I can make it a little bit. Okay. Okay, that's the person number. Here is the conditional probability. This is what we calculated. This is the probability of UN given previous guys. People are unique. So this is exactly the thing that was 365 minus something divided by 365. So for the first person, it's literally 365 divided by 365, 100%. For the second person, it's 365 minus 1, all divided by 365. And the pattern is it always goes down by 1. So the first person the second person who walks in the room has a 99.7% chance of having a unique birthday, and so on. How do I enter this into my spreadsheet? You put in 365 minus the number of people minus 1 divided by 365. And hopefully that's right. Did I get it wrong? You have to add 1. Okay. Okay, you know what? I'm gonna do a sneaky. I'm gonna make it minus this one. Okay. There we go. So it's always like this is minus the third person is 365 minus 2, and so on. So this is the formula we did before. I'm gonna drag this one all the way down to my people. Okay. You guys with me so far? All right. This is maybe where, there's a secret code word you need to know in Excel, or I guess Google Sheets in this case, to do this one. This is going to be the product of all the branches. So this is what I want this to be. Product along branch. And so what I want this to be is the product of everything before it. So the first one is 100%. The next one is the product of this times that, right? The product of the first two. The next one is the product of the first 3. So it'll be B2 to B4. Okay. And now it's tempting to take this and drag it down like we have been. But is that the right thing? Well, let's drag it down one more, and you'll see. Maybe it suggested what I want. Okay, well, if you drag it down, you might just get the product of the previous 3, which is not what you want. So there's a secret thing in Excel, which is the $sign. So if you put in a $sign, that will tell it always start at row 2. So if you put in B $2, it will always start in row 2, even as you drag down. Who knows about the secret $sign in Excel? Who's never heard of the $sign? Okay, now you guys are learning, see? So you're learning. The $sign makes you always start. Whatever you put in front of the $sign will not adjust as you go up and down. Yeah, the problem is the AI these days knows everything already, so sometimes it'll just do it for you. But okay, if you do B $2, that means always start in row 2, and this should work. So I'll just drag this down. Okay, and let's just check the last one. You see the last one is still B $2 up to B30. It's the product of the first 30 rows. And this is the actual conditional probability they're all multiplied together. This is the probability they all have unique birthdays. They all have unique birthdays. Okay, and that's the answer. So, we did it for 3 people. For 3 people, the answer is 99.1%. So 3 people in a room, 99.1% chance. If you have 10 people in a room, it's down to an 88% chance. So there's sort of a 12% chance that if you have 10 people in a room, that 2 of them will have the same birthday. And you can sort of see how this number is getting smaller and smaller, and it all of a sudden shrinks very quickly. The way you can visualize this is to graph it. So let's graph it. You do this and this. Give me this and that one. And now I want to graph it. So I go to Insert, Chart, and oh, there's my beautiful chart. Okay. All right, and let's look at this chart. So when you have only one person, there's a 100% chance, but it quickly goes down, and it crosses 50%. That would be half the time they're all unique, half the time there's a repeat birthday. It crosses that at 22 people. So 22 people is slightly more than 50%. They're all different. And 23 people is slightly more than 50% that somebody has a repeat birthday. So this picture is the kind of answer to typically how big do you need it to be? You only need 23 people in the room, and then you're 50-50 that somebody will share a birthday. on the first day of class, I made you guys do this. Let's drag these things down a little bit more to get more people. So there's like 100 people in the room, right? Right now in the class, ish. Can I make the chart again? Okay, let's make it again up to 100. So some people, I remember on the first day of class, they were like, oh, you're assuming that of the 100 people that come to class today, they actually do have the same birthday. Like somebody has the same birthday. And if you look at when there's 100 people in the room, there's really like very close to a 100% chance that two people share the same birthday. The chance of having like 80 people in the room and everybody has a unique birthday is super, super close to 0. So it goes down really fast. Once you're at like 60 people, it's like basically impossible that people won't have the same birthday, which is really surprising. You think there's like 360 days in a year, you only need 60 people in the room before you're pretty sure, like very sure, that two people have the same birthday. Okay, and it goes down like, yeah, like with 50 people in the room, there's only a 2.9% chance that people all have different birthdays. Okay, that's the solution to the birthday problem, and we did it in with the computer and with our probability trees. Questions or comments about any of that? Okay, so we're gonna keep going with probability trees, and we're gonna sort of take it up a notch. So the probability trees up until now, they're the kind of thing you can sort of stare at and just like know the answer. Like you really look at the tree and you do what it is. I guess the very last thing we did, we kind of like did this ... business, right? So we were like, oh, I kind of see the pattern, I continue the pattern. So we're gonna be starting something which are probability trees where you just count them up. So let's call this like fancy probability trees or something. Fancy probability trees. And this is what happens when your probability tree is like too big to like write everything down, but you can sort of just imagine it, and by imagining it in the right way, you can sort of like roughly count things up. So you can kind of say like, oh, it kind of does this and then that. And sometimes people call this thing enumeration. Enumeration is a fancy word for counting things up. And sometimes people call this combinatorics, although combinatorics is a bunch of other things as well. So combinatorics. But this is like part of combinatorics is enumeration. And to give you the very first example, I have a new source of probability. So far we've done cards, we've done dice, we've done people walking in the room, and the new source today is this thing. Does anyone know what this is? Who knows what this is? Yeah. It's bananagrams. Okay, I thought somebody would say it's a banana, but it's not a banana. It's bananagrams. So bananagrams is this game. It's a little bit like Scrabble. You have these tiles. Let me turn this on. That'll be fun. Is this on? Okay. Let's try this. Okay, here we go. So you have these little tiles. And it's like Scrabble, but it's more fun than Scrabble because you don't have to keep score. So there's no numbers on them. You just try to make words, and it's a lot of fun. And here's the first little question you can ask about bananagrams. So I wrote it down as Scrabble. I was not confident everyone would know what bananagrams is. So I said Scrabble. But you try to make words. You do the same thing in bananagrams. And here I have the 4 tiles, I-L-S-T. And here's the question. There's 5 words you can make. You can make the word litz. Okay, there's 5 words you can make that include all 4 letters. Litz or stilt. And over here I have them all listed. I didn't know all these. I used the internet to find the answers. Tills. Okay, I guess that's like when you dig and you're like a farmer. Okay, so the question is, if I shape these up, actually right before class I noticed there's a cup of lost pencils from students. So we're going to dump that out. Put the tiles in here. So we shape these up, and we're going to put them out one at a time. S. I. Oh, it could happen. T. L. Siddle. Not a word. Not a word. So the question is, what is the chance it is a word? Okay? And you can solve this problem using a probability tree. So draw a probability tree. Maybe you can't fit the full probability tree on your page because it's pretty big, but you can at least like sketch it out, and then you can use that to find the answer. What's the probability when I shake it up that I get an actual valid word? And maybe one side of this fraction is easy and one side is hard. You should at least be able to figure out one side. But I'll give you guys a couple minutes, and then I'll show you the answer, and that's going to lead us into our next topic. And you'll see that we're just doing fancy probability trees. All right, let me set you loose for like 3 minutes here. Figure it out.
Just do this. That's the total number of words you can make divided by what the number of actual words are versus divided by the total number of different things you have. It's 4 factorial. But I'm not doing my 20. It's 4 times 3 times 2 times 1. So 24. There's 4 options for the first one. This is 5 and 24. I think that makes sense. 5 and 22.
Okay, there's like 30 seconds left. Once again, I do want to take the temperature of the room and see how you guys are doing. So put it on answer. Even if you don't know the exact answer, maybe you know like half of the fraction. Maybe you know just the top or just the bottom. Feel free to put in one of those. You can put in 111 on the one you don't know. I'll give like an extra 30 seconds so you can put in your final answer. But I do want to see where you guys stand. Okay, 5 seconds left. Get in your final guesses. Final guesses. Waiting for the last couple of stragglers to get in. Okay, I'm pressing the button. I'm doing it. Okay. Let's try this button. Submission counts with labels hidden. That's exciting. So 43 people said something. 16 people said something else. So about half the class maybe knows the top, but at least no clear consensus on the top there. I guess people are leaning one way. What about the bottom? The bottom. Let's look at the bottom of the fraction. The bottom of the fraction, 48 people put. Okay, that's exciting. Okay, let's see what people actually said. Okay, on the top, people said 5 or 111. Just over half the people said 5. 5 is the right answer. If you said 5, it's 5. 53. Okay. I don't know how you get 53, but maybe it's possible. Okay, 5 is the right answer for the top. Why is 5 the right answer for the top? It's because there's 5 words you can do. And you'll see that at some level, probability with this kind of stuff is always counting the number of ways something can happen divided by the total number of ways. And in some sense, there's 5 things that can happen. So 5 is the right idea. If you want to actually put together a full argument and get the 5, it's a little bit more work, but you kind of know what you're aiming at if you got the 5. And on the bottom, what's on the bottom is the most common answer, 111. Okay, no, it's not. It's 24. So just over half the people have 24. That is also the right answer. So about half the people kind of maybe have seen this before or know what's going on. 60% and 63%. Okay. So why is it 5 and 24? That's what we want to do. And I'm going to do it. Actually, okay, this is good. I think it's good if you guys are like explaining to each other what's going on. Why don't I give you guys all 1 minute to talk, and then I will tell you my version. But do the student version. Talk to your neighbor. Like they probably have a better answer than me. Okay, let's come back together, and I will tell you my version of why it is 5 over 24. And there's actually, I have 2 sort of, quote, completely different ways to see why it is 5 over 24. So the first way is kind of what we just did. You can draw a probability tree that looks exactly like the probability tree that we did for the birthday problem. The only issue is you can only do this for 1 word at a time. So let's pretend the question wasn't what's probability of making any word. Let's ask the question, what is the probability of list? Like exactly the word list. If you get the word tills, doesn't count. What's the probability of exactly the word list? And to get the word list, 4 things have to happen. First, you have to get L. Then after you get L, you have to get I. Then after you get I, you have to get S. Then after you get S, you have to get T. So you can write this as a big tree. So first is list. First is L. Then the second has to be I, given that the first is L. Then the third has to be S, given the first is L and the second is S. And the fourth has to be T, given the first 3 are exactly the things. Okay, I'll just write first, second, third, and you fill in how much detail you want there. Hopefully it makes sense. And this is exactly the probability tree of, did you get an L or did you like fail? Right? Or did you, and then you got an I, given that you got the first thing and then you fail. Or an S and a T. So you kind of have this probability tree of the first 4 letters, just like you had a probability tree for all the people getting the same birthday, or all the people, I guess, having different birthdays, rather. Different birthdays, or different suits, or whatever. And the first branch here is a quarter. There's a 1 in 4 chance the first one is an L. Given that the first one is an L, the second branch has a probability of a third, because there's 3 tiles left, and one of them is the one we want, and then a half, and then this one is definitely going to happen. That's the last tile. So it's a quarter times a third times a half times 1. That is this way to do it. So a quarter times a third times a half times 1. So if you just had one word at a time, the probability is a quarter times a third times a half times 1 by the tree that we just did. I'm guessing most people did not do it this way. Who did it this way? A few people. The reason most people don't do it this way is they take some course in like high school and they're like, just memorize this stuff and do it this way. Who memorized some stuff from high school and that's how they did it? A few people. Okay, maybe less people than I thought. All right, so this is one way to do it, to get the word list exactly. And then if you want to know what is the probability for all of the words, so probability of list or, remember union is or, list or silt or whatever the other 5 words were. What's the last word? Tills. I don't know. It's going to be the sum of all these. You can't, these are disjoint events. You can't be both list and silt. So you add them up. This is the sum rule for disjoint events. Sum rule. Which says it's the probability of list plus the probability of silt plus ... plus the probability of tills. And each one of these is 1 over 24. There's 5 words. So the answer is 5 over 24. So that is the full solution of the first way to do it. You make a tree like this for one word, and then you add them up. Okay. This is probably not how you did it. There's a kind of a more straightforward way, but I wanted to show this way because it connects to what we did before. And actually, it's like very similar to what we're about to do in Disguise anyway, so it's good to know. Questions or comments about this way to do it? Like I said, the thing I love about probability is there's more than one way to do a problem. There's not just one way. Okay, here's the other way. You draw giant tree, the giant tree way. Okay, and in your giant tree, you keep track of all the possibilities. So it could, the first one could come out L, I, S, or T, right? That's the 4 possibilities for the first letter. Then each of those has 3 possibilities for the next letter. Let's do that in a different color. So we maybe try to keep it a little bit more organized. 1, 2, 3. It could be I or S or T. Or here over here, it could be L or S or T. Here it could be L or I or T. And here it could be L or I or S. That's 2 layers deep. I'm going to draw the third layer. There's 2 branches coming off. Who did the problem this way? Who drew a big tree like that? Okay, almost everyone. This is a great way to do the problem. All right. So S or T, I or L. Okay, what's left? I or S. All right. So you see it's getting quite tedious already. I'm just going to draw the rest. You're going to have to use your imagination for what they are. But I will draw 2 branches coming out of each of them. And you see they're getting squeezed because there's sort of exponentially many of these and only polynomially space on the paper. Okay, but that's your tree. Actually, there's one more, right? The last letter is fixed. There's one choice of what the last letter will be. What the last letter will be for each of these. Okay, here's my giant tree. This is the biggest tree I'm ever going to draw because this is too much for me. I'm getting lazy already. I can feel it in my bones. Okay. Here we go. There's my tree. So you have this tree, and the point of the tree is you can figure out the probabilities by multiplying along each branch. You will see that each branch is 1 over 24. So each branch has probability 1 over 24. Why is it 1 over 24? Well, it's a quarter times a third times a half times 1. That's why we just did that. Right? A quarter times a third times a half times 1. That was, we kind of drew over here. This is one particular branch of the tree. It's actually, I think, the top branch. Yeah, the very top branch is what we drew right here, L-I-S-T. Right? So kind of what we drew before was like a really compact version of this whole tree where we said you're either on the critical path here for the word list or you're off of it, and whatever you do wrong, as soon as you leave this thing, you fail. That's all we got to keep track of. So this is like a compact version of this thing, and you see that the branch has probability 1 over 24. There's another easy way to see why the probability of each branch is 1 over 24. Did anybody reason a different way? Yeah.
So based on the words and what letter they start with, let's see like the probability of words starting with that letter. So like
Yeah.
a word starting with S, there's probably a 2 out of like 6.
Oh, okay. So you looked at like the two words that start with L. I think are silt and slit, maybe.
Yeah, and then
Ah.
2 to 6, and then there's 0 that start with I, 2 that start with L, and 1 that starts with T.
Okay, I love that. So you're kind of doing like a little case analysis. Like you're looking inside each one, and you're like, there's two good words here. Here, right? Okay. And then how many were there in the other ones?
0 in I, 2 in L, and 1 in T.
1 in L and 2 in T.
Other way around.
Okay, 2 in T. Okay, this is great. Very nice. Okay, and then how do you know the probability of each word? Like, I said it was 1 over 24 by doing this.
Well, so their denominators in each section are a 6, and so you just add them all together.
I see. Okay, so you figured out each one individually, and then you added them up. Right. Okay. So that's a great solution. So you're going to add them up. There's going to be 5 total. So the thing you got to know is how much each one is. And I said it's 1 over 24 by doing this a quarter times a third times a half times 1. But there's a total other way you could get the answer 1 over 24. Yeah.
There's 24 ways to arrange the letters, and only 5 of those arrangements are words, so it's 5 out of 24.
Yeah, so there's 24 arrangements of the letters. That is a great way to do it. The number 24 is also something else that's already on the board. Like, I 100% agree with you. Do you see where is the number 24 on this board?
The number of green lines.
The number of green lines, because every green line here, every end of the tree is exactly, going back to the root, is exactly one way to arrange the letters. So you're saying there's 24 ways to arrange the letters. That's the same thing as saying there's 24 paths on this tree. And it's exactly for the reason you said. There's 4 choices in the first branch, then 3, then 2, then 1. 4 times 3 times 2 times 1 is the 24 is the number of choices here. So you could say it's 1 over 24 by doing a quarter times a third times a half times 1. Or you could say there's 24 total because it's 4 times 3 times 2 times 1. And then the last thing you got to do is notice that there are 5 good branches. So you could break it up by where they are. So you could say 2 here, 0 here, 2 here, and 1 here. But the only thing that matters is there's 5 of these branches. 5 of them somewhere are the words we want. There's 24 total. So the answer is going to be 5 out of 24. One last important thing I want to tell you, and the reason we're doing this, is this 24 idea is so common, it has a name. And you must know the name. The name is factorial. Factorial. And factorial looks like this. You write 4 factorial. That means 4 times 3 times 2 times 1. This is the number of branches in this kind of tree. Okay. So you have to know this name, this exclamation point. It's a really common math notation. And I tried to do it slowly so you guys would see like where it comes from. It's not magic. It really just comes from this idea. We're going to learn more crazy notations on Monday. So yeah, see you guys on Monday when we come back.
There's a number. Number greater than 2. Maybe
You could write the sum using secret notation. Yeah, so I just said there's 5 of them somewhere. If you want to write them all out, you can do that too.